Alright guys, welcome back to Underground Science, and today we'll be talking about beta negative decay. Alright, and beta negative decay is just one of the many types of radioactive decay. Alright, and atoms will undergo radioactive decay if they're not stable. Alright, if the nucleus of an atom is unstable, it's going to undergo radioactive decay and try to become more stable. Alright, so beta negative decay, the basic idea behind beta negative decay is that the nucleus of an unstable atom will eject an electron, alright, to become more stable. Alright, and now you're probably wondering, well, what determines if the nucleus of an atom is stable or not? Well, if most of the time, if you calculate the neutron to proton ratio of an atom's nucleus, and if that neutron to proton ratio is in between the range of 1 to 1.2, then that means that that atom's nucleus is stable and most likely will not undergo radioactive decay. All right, and this range that you see here can sometimes vary in other websites and textbooks, but for the sake of this video, we'll go ahead and use this common range here to tell if the nucleus of an atom is stable or not, and this ratio is for the neutron to proton ratio. All right, so again, if you calculate the neutron to proton ratio and it's in between this range right here, 1 to 1.2, it most likely means that that atom is stable and most likely will not undergo radioactive decay. All right, so let's go ahead and jump into our first problem for beta negative decay, our first example. All right, so our first example we're going to jump into, let's do in a different color, will be carbon 14. All right, and if you watched my mass defect video, you would know how to calculate the number of neutrons, protons, and electrons an atom has based on this notation right here. So if you haven't already, go ahead and watch that video, but I'll quickly explain it again here. So to calculate the number of protons and electrons an atom has, all you have to do is just look at the atomic number. All right, so this is the atomic number denoted as Z. And if the atom is neutral, it means that this atom has 6 protons and 6 electrons. All right. If it's neutral, if the atom's neutral, then it's going to have 6 electrons. All right. If the atom has the same number of protons as it does electrons, it means it's neutral. All right. And we don't see any formal charge here in carbon 14. So that means carbon 14 is neutral and will have 6 electrons and 6 protons. And then to calculate the number of neutrons, right, you just do the mass number minus the atomic number. All right. So mass number denoted as A, right? So let me go ahead and write that down here. The mass number is A. And you do the mass number minus the atomic number. So that's going to be 14 minus 6, or 8 neutrons. All right, so let me go ahead and write it below there, so it's going to make more sense. 8 neutrons. So carbon 14 has 6 protons, 6 electrons, and 8 neutrons. All right. And with our protons and neutrons, we can go ahead and, before we show the beta negative decay, we can go ahead and calculate the neutron to proton ratio to see if carbon 14 is stable or not. All right, so neutron, so let's go ahead and scroll down a little because running out of space. So the neutron to proton ratio, right? Neutron to proton ratio for carbon 14 is going to be, we just calculated neutrons, which is 8 divided by the proton ratio, which is 6, which equates to about 1.33 repeating. All right. And remember right here, we said that the stable range for an atom's nucleus is about 1 to 1.2. All right, the neutron to proton ratio. Well, right here we see it's greater than that. It's greater than the range between 1 to 1.2, so that means carbon 14's nucleus is unstable, so it will undergo radioactive decay. And in this case, let's show beta negative decay. All right, so carbon 14 will undergo beta negative decay. All right, beta negative decay. And what happens in beta negative decay, as we said above, it's the nucleus of that atom is going to eject an electron. Now, to be more specific, a neutron in the nucleus will eject an electron. All right, so let's show that in another color. So a nucleus, or a neutron in the carbon-14's nucleus, right, I should say, is going to eject, oops, that's not a good zero. Sorry about that. All right, is going to eject an electron, and that neutron is going to turn into a proton. All right, so what's going to happen is, remember, a neutron has no charge. All right, and so you could think about it like this. Let's say you have a lot of stress, right? And that stress, let's say, is a negative charge. And someone comes in and sucks all that stress away from you. So all that negative charge that you had is gone, and now you're more positive than you were. Right? Just like that, a neutron will eject its stress, right? In quotes, just like we just said for our analogy, will eject its stress or its negative charge in the form of an electron. And by doing that, the neutron is going to become more positive, or as we say, the neutron is going to turn into a proton, which is a positive charge. So now we're not going to have 6 protons like we did before, right? We're going to have 7 protons. And why? Because the neutron is going to turn into a proton, all right? Because a neutron in the carbon-14's nucleus ejected an electron, becoming more positive, or as we would call it, becoming a proton. So now this unknown atom that we don't know yet has 7 protons now, all right? And the mass number of this unknown atom is 14 still, all right? It's still 14 because, here's the thing, right? Before we had 6 protons in carbon-14, and then we said we lost a neutron because a neutron turned into a proton, all right? So what happened here, right? We gained a proton, and then we lost a neutron, right? Because that neutron turned into a proton. So that's why the mass number stays the same, because we did lose a neutron, so you would think that the mass number would decrease, but then we gained a proton instead, all right? And actually, the mass of a neutron is 1.009 atomic mass units, and the mass of a proton is about 1.007 atomic mass units. So you can see the two masses are almost the same. So that's why the mass number stays the same, because we just lost a neutron, but then we gained a proton instead. All right, and then now to find out what this atom is, right, of 7 protons, the atomic number of 7, just go to the periodic table and look at which atom or which element has an atomic number of 7, and you'll find that it's nitrogen. All right, so carbon-14 underwent beta negative decay, which is a form of radioactive decay, by ejecting an electron, and it became nitrogen-14. All right, remember we said that the purpose of radioactive decay was so that the nucleus can become more stable. Here in carbon-14, we saw that the nucleus was not stable because the neutron to proton ratio was 1.33, repeating, which is greater than about 1 to 1.2, which we said right here. This determined our stability, all right? Now let's calculate the new neutron to proton ratio for nitrogen-14. All right, so remember, 14 is the mass number, 7 is the atomic number. And to find the number of neutrons an atom has, you subtract those. So mass number minus protons is equal to 14 minus 7, which is 7. So that means nitrogen-14 has 7 neutrons. All right, sweet. How many protons does nitrogen-14 have? Well, you just look at the atomic number to find that out, which is 7. So nitrogen-14 has 7 protons. Then you go ahead and divide that to find the neutron to proton ratio, and you find out that it's equal to 1. And now we see that nitrogen-14 is stable because the neutron to proton ratio is 1, and over here in the beginning of the video, we said that the range should be about 1 to 1.2. Again, it can vary, all right? But we see that 1 is obviously stable because it's been between 1 to 1.2. All right, so we just saw that carbon-14 right, went from a unstable nucleus, which is right here, and it radioactive decayed in the form of beta negative decay, and it turned into a stable nucleus, which is the whole goal of radioactive decay. Alright, so that was one example of beta negative decay, and let's look at another example of beta negative decay. And this example is going to involve thorium-234. Alright, so thorium-234. And if you go ahead and look in the periodic table and you see how many protons does thorium-234 have, or just look at the number of neutrons, or the atomic number, right? We're going to calculate the number of neutrons later. But if you go to the periodic table, you'll see that thorium-234 actually has 90 protons because of the atomic number. All right, so now to find the number of neutrons, right, that I just mentioned like a couple of seconds ago, you would have to subtract the mass number minus the atomic number. And if you do that, so 234 minus 90, right? Remember again, this is the mass number. Remember, we're finding the number of neutrons, all right? So mass number minus atomic number, you're going to get 144 neutrons. And this is the amount of neutrons thorium-234 has in its nucleus. Remember, we're dividing neutrons to protons to find the neutron to proton ratio to determine if thorium-234 is stable or not. All right, so to find the number of protons, you just look at the atomic number, right, the Z, which is the way you denote atomic number, and we see it's 90. So thorium-234 has 90 protons. All right. So now that we have this, let's calculate it. And if you divide 144 over 90, you're going to get a value of about 1.6. All right. So this is the neutron to proton ratio for the nucleus of thorium-234. And right away we know it's not stable. The nucleus isn't stable because it's greater than our range that we said for stability, which was 1 to 1.2 about. All right. So now we know it's going to undergo radioactive decay, and in this case, beta negative decay, so let's see what happens. All right, so let's go ahead and write it down. What's happening? We're undergoing beta negative decay. All right, so again, the same thing's going to happen. The nucleus of thorium-234, in particular, a neutron in the nucleus of thorium-234, all right, will eject an electron. Oops. Will eject an electron. And by the way, to tell what this notation means, the bottom number right here is, or represents the charge, all right, of -1, which we know is a charge of an electron. And the top number represents the mass of an electron. And the mass of an electron, the reason why it says 0 is because it's very close to 0. All right, the actual mass of an electron in atomic mass units is about 0.0005 atomic mass units. So we can see that's very close to 0. All right, so what's going to happen now? All right, so we saw thorium-234, a neutron ejected an electron, and as we said before, when that happens, that neutron is going to turn into a proton. So what we're going to see here is an atom right now that we don't know, which will have 91 protons now, right? Because we just gained a proton because of neutron ejecting an electron turning into a proton. And the mass number will stay the same because although we did lose a neutron, we also gained a proton. And we showed right here that the masses of a neutron, or the mass of a neutron and the mass of a proton is almost the same. So the mass number will stay the same. And then if you go to the periodic table and you go look at which element has 91 protons, you'll find that that element is protactinium, right, which you denote as Pa. So let's go ahead and calculate the new neutron to proton ratio for protactinium-234 and see if protactinium-234 is stable or not. So again, we're going to subtract the mass number minus the atomic number to find the number of neutrons. And if you do that, you're going to get remember, we're losing 1 neutron here. So we just have to minus 1 neutron from 144. So we're going to get 143 neutrons for protactinium-234's nucleus. And then we have 91 protons in the nucleus. And remember, the protons and neutrons make up the nucleons. All right. So I talked about that in my mass defect video. So we have 143 neutrons and 91 protons. If you go ahead and divide that, you'll find that the neutron to proton ratio is about 1.57. So right away we see that protactinium-234 is still not stable. All right, the nucleus of protactinium-234 is still not stable. And that means what? All right, it's going to keep on undergoing radioactive decay until the nucleus becomes stable. All right, until the neutron to proton ratio is in between about 1 to 1.2 or greater. Like some textbooks and websites can say 1 to 1.4 or 1 to 1.5. But for this video, we're going to use 1 to 1.2. All right, because this can be written as the most common range when determining if the nucleus is stable or not. So actually what happens next is that protactinium-234 can undergo beta negative decay again and turning into uranium-234. So let's see how that's going to work. All right, so let's write down protactinium-234. Let's do black. Protactinium-234 with 91 protons will again undergo beta negative decay. All right, beta negative decay. And what's going to happen is, again, a neutron is going to eject an electron, turning into a proton, which is why we're going to have 92 protons now, staying the same mass. And if you go to the periodic table and see which element has 92 protons, you're going to find that it's uranium. All right, and if you go ahead and calculate the neutron to proton ratio for this, you're going to find out that it's equal to about 1.54. All right, and again, we did that by subtracting the mass number. And so you've subtracted 234 minus 92, mass number minus atomic number, to find the number of neutrons, and then you divided the number of protons. So you did mass number minus atomic number, which was 142. All right, so uranium-234 has 142 neutrons, and then you divided that by 92, and you got 1.54. And 1.54 again is still not stable. So it's going to keep on undergoing radioactive decay, maybe alpha decay next. It's going to keep on undergoing radioactive decay until the nucleus is stable. That's the whole goal of an atom, to become more stable. All right, so that's our second example. Let's look at one more example of beta negative decay, and then we'll end the video. All right, so let's talk about tritium now. All right, so tritium is one of the 3 isotopes of hydrogen. All right, let's not write, nope. Let's go ahead and write a better 3. There you go. All right, and the neutron to proton ratio for tritium, we can go ahead and calculate real quick. We should be good at calculating this by now, right? Mass number minus atomic number, which is 2 neutrons for tritium's nucleus, divided by 1 proton because of the mass number, right? And that equals 2. Again, 2 is greater than our range that we said, which is 1 to 1.2, which means tritium's nucleus is not stable. So we're going to draw a beta negative decay reaction, right? Beta negative decay. And we said that what happens, right? A neutron's going to eject an electron, becoming a proton, staying the same mass number because, remember, a neutron and a proton have almost the same mass and they replace each other. All right, and now what's going to happen is if you go to the periodic table, you look at which element has atomic number of 2, you're going to find that it's helium. Now we're just like, all right, sweet, let's go ahead and calculate the new neutron to proton ratio for helium-3 and see if helium-3 is stable or not. All right, so let's go ahead and do that. Again, we do the same exact thing, right? Mass number minus atomic number, we get a value of 1 neutron divided by the number of protons. Well, all right, sweet, let's just look at the atomic number, which is 2. So we get a neutron to proton, oops, this was a capital. Go ahead and erase that real quick. we get a neutron to proton ratio of 0.5. Now right away, I'm thinking too, I'm like, all right, so this is not stable, but we have to correct that thought because helium-3, which is right here that we used in this example, helium-3 and protium, which is another isotope of hydrogen, are two exceptions when we look at the range. All right, even though helium-3 is 0.5, which is below this range right here in determining stability of the nucleus, it still counts as stable because helium-3 will most likely not undergo radioactive decay. Again, because it's an exception. All right, so radioactive decay. And again, if you can even test this out for protium, right? The number of neutrons protium has is mass number minus atomic number, which is 0. And then you divide that by the number of protons, which is 1, right? Which is going to be 0. And 0 is obviously less than this range right here. But it still counts as stable, or protium is still stable because it's an exception. So also protium will not undergo radioactive decay, right? Because it's stable. Radioactive decay, even though it's 0, right? Even though the neutron to proton ratio is 0, it's an exception, right? So protium and helium-3 are exceptions. And guys, that's pretty much it for beta negative decay, right? All just at least take away from this video is that the main idea behind radioactive decay is that that's what an atom is going to undergo in order to become more stable. And the main idea behind beta negative decay is that the neutron or a neutron in an atom's nucleus will eject an electron to become more stable. All right. So, and you can calculate stability by calculating the neutron to proton ratio, but we just saw that sometimes that doesn't work, especially for our exceptions, which we said were protium and helium-3. All right. And while we're at it, let me just tell you the last isotope of hydrogen, right? We just said protium and tritium were 2 isotopes. There's actually 3. So the third isotope of hydrogen is hydrogen 2, all right? And this is also called deuterium, right? And hydrogen 2 right here, you can see that has 1 proton, 1 electron, and to calculate the number of neutrons, we should know by now is mass number minus atomic number, right, which is 1 neutron. All right, so that's it for this video. My next video, I'll probably be talking about beta positive decay, right, which is just another subtype of beta decay as a whole. And beta positive decay is also called positron emission. It's another form of radioactive decay, and that's probably going to be the topic of my next video. So make sure to stay tuned and don't forget to hit that notification bell, all right, so you know when I'm publishing my videos, and don't forget to subscribe and like, all right? See you guys.